So far, we have been hyper-focused on propagation of closed orbits, but now let's take a look at propagation of open orbits. And we'll start with parabolic orbits, which are actually surprisingly straightforward as compared to elliptical and hyperbolic ones. Remember that for a parabola, the semi-major axis is no longer defined. It's effectively infinite, and the eccentricity is exactly equal to 1. However, the conic section equation is exactly the same as before. So we'll start with that. The orbital radius for all time is given as h squared over mu divided by quantity 1 plus e cosine nu. E, as we just said, is 1. And so what we have is where we've used the trigonometric identity to change this denominator into this factor. Remember, the angular momentum is equal to r squared times the time derivative of the true anomaly, and is also equivalent to the square root of the product of mu with the semi-parameter. So if we make the substitution and integrate this expression with respect to time, what we will get is the mean motion on the parabolic orbit times t minus the time of periapsis passage is equal to b plus b cubed over 3, where b, sometimes known as Barker's anomaly, is defined as the tangent of the true anomaly divided by 2. And n sub p, the mean motion, is equal to twice the square root of the gravitational parameter divided by the semi-parameter cubed. Note that for a parabola, the radius of the periapsis passage is just half the semi-parameter. So here we have a setup that looks very, very similar to the eccentric case, except the right-hand side is no longer a transcendental expression in this new auxiliary anomaly, B. Instead, it's a polynomial expression, and because it's a polynomial of order 3, it has an exact solution. And in general, we can write for a parabola that is, the change in time is equal to 1/2 the square root of L cubed over mu times b plus b cubed over 3 minus b naught cubed over 3, where b is the parabolic anomaly at the final time and b naught is the parabolic anomaly at the initial time. And this is generally known as Barker's equation. So of all possible orbit types, circular orbits and parabolic orbits are the only ones that are trivial to propagate, because in the case of circular orbits, you are moving at constant velocity for all time, and so your mean anomaly is equal to your eccentric anomaly for all time, and there's nothing to invert. And for parabolic orbits, there's a polynomial expression that can be solved exactly. When we turn to the hyperbolic orbit case, it turns out that we can set it up exactly in the same fashion that we did for elliptical orbits, except that we have to define an anomaly, a hyperbolic anomaly, in terms of an area rather than an angle measure. We define the hyperbolic anomaly h via the area of the shaded region, and this area is the region between the vertex of an equilateral hyperbola and the center of the hyperbolic figure up to the point that is a height above the location of the orbiting body on its true hyperbolic orbit. So very analogous to what we did with the auxiliary circle and the definition of the eccentric anomaly, except here we have an area and we're defining an equilateral or right hyperbola rather than an auxiliary circle. If this shaded region is defined as the semi-major axis squared times the hyperbolic anomaly over 2, then what we get are sets of expressions that are identical to the ones that we got for ellipses, except that they are all in terms of hyperbolic functions rather than trigonometric functions. But other than that, things are exactly the same. And the time equation that you get also looks exactly the same, except for it's a flipped sign, where n sub h, the hyperbolic mean motion, which is given by the square root of negative mu over a cubed, because recall that for hyperbola, a, the semi-major axis, is defined as being negative. So this has to be a strictly positive quantity, and inside the square root, hence the negative sign. The hyperbolic mean motion times the time since periapsis passage is equal to the eccentricity, which is a quantity greater than 1, times hyperbolic sine of the hyperbolic anomaly minus the hyperbolic anomaly itself. And you can apply Newton-Raphson iteration to solve this exactly in the same fashion as you did for the ellipse case.